sorry, I've been recording. 3/2 to 2 of our function. And so that's going to be 2/3, and then M3 would be the supremum from 2 to 4, which would just be equal to 1/2. So we get these maximums for our function on each of these subintervals. And then the upper sum is just the sum from k equals 1 to 3 of these supremums times, x of k minus the distance, the width of our subintervals. So in our case, then, when k is equal to 1, we plug that in. M sub 1 is equal to 1. So we have 1 times the absolute value from 3/2 minus 1 plus 2/3 times the absolute value of 2 minus 3/2 plus 1/2 times the absolute value from 4 minus 2. 4 minus 2. We add that all up, and that gives us our upper sum. So we have 1/2 plus 1/3 plus 1, and so we end up with 6, 8, 11/6 showing up. And same kind of picture, except that now we've taken the maximum of the function instead of the minimums. And so now we are looking at these rectangles, which are overestimates of the area. So, any questions about computing lower sums, upper sums, what they mean, how they relate to just our geometric idea of what an integral is? Anything in there that needs clarification? All right, so what we are interested in is the real definition of the integral. We have these upper sums and these lower sums, and then what we do is we come up with the upper integral. And the upper integral, which the book uses u of f to be the upper integral, that, remember these are the upper sums, that's the infimum over every possible partition of our upper sums. So here this puffy p is the set of all partitions. So we calculate basically every possible upper sum that there is, and then find the infimum of those, and that's what we call the upper integral. And then we have the lower integral, which is the same thing, except now we want the supremum of all of the lower sums. And then we say that the function is integrable if the upper integral and the lower integral are equal to each other. And we say that the value of the integral is equal to whatever that value is that those two are both equal to. So that's the Riemann integral. That's Riemann's definition of what an integral is, and in essence how to compute one, although it's really not a recipe for computing it, since we're looking over every possible partition, and there are infinitely many possible partitions, so there's no way we're actually computing an integral doing this. But that's the idea. Theoretically speaking, that's what we're doing. So, any questions about that, about the definition? All right. So, what we're interested in then is refining these partitions and seeing what happens as we refine the partition. Remember, the refinement of a partition just means we're adding points to it. So we can come back to this partition that we have here, and we can create a refinement for it by adding some more points to it, or at least one more point to it. And so we can come up with a new partition, we'll call it P prime, which is a refinement of this partition. So it has to have all of the points that this partition has. So it has to have 1, has to have 3 halves, has to have 2, has to have 4. Every partition has to have 1 and 4 in it. And then to be a refinement, it has to have all of the points of the previous partition. And then to refine it, I just need to add at least one more point. So let's just throw 3 in here. That's what the book asks us to do. And so this is a refinement of our partition P. It's got more points in it, has the same number of points plus some more, so that's what we call a refinement. And then what we want to do is go back and say, well, okay, so what happens to our upper sum and our lower sum as we create this refinement? Now, I'm going to go through this much more quickly. We just remember that 1 over x is monotone decreasing on this whole interval, and so the infimum is always the right end point of the subinterval, and is at the right end point, and the supremum is always at the left end point. And so when we go to calculate the lower sum relative to this new partition P prime, so that's going to be our sum. We take the infimum over the first. So, you know, our subintervals are here from 1 to 3 halves, from 3 halves to 2, from 2 to 3, and from 3 to 4. And so on this first subinterval from 1 to 3 halves, the infimum is 2/3. And then the width of that subinterval is 1/2. So we take the infimum times the width of the interval, plus, then we go look at the second subinterval here from 3 halves to 2. The infimum on that is going to be 1/2, and the width of that interval is 1/2. Then we go from 2 to 3. The infimum there is going to occur at 3, so the infimum is going to be 1/3, and then the width of that interval is 1. And then we look at the subinterval from 3 to 4. The infimum of the function on that interval would occur at 4, so that would be 1/4, and the width of that interval is 1. So if we look at this particular partition, we've got 1/3 plus 1/4 plus 1/3 plus 1/4. So basically we've got 2/3 plus 1/2. So that is 4/7/6. And then if we look at the upper sum on this new partition P prime here, now we're looking, it's going to be, the widths of the intervals are going to be the same, but now we're looking for the maximum or the supremum of the function, which is going to occur at the left endpoint. So on this first subinterval from 1 to 3 halves, the supremum would occur at 1. And when you plug 1 in, you get 1. And then the width of the interval is 1/2. Supremum over the next interval would occur at 3 halves. So the supremum would be 2/3. Width of the interval is 1/2. Supremum over from 2 to 3 is going to occur at 2, so that's going to be a half times 1, and then the supremum over this last subinterval from 3 to 4 would occur at 3, so we would have 1/3 times 1. So our upper sum now is a half plus a third plus a half plus a third, and so now we've got 1/4 plus 2/3, I don't know, 1. So it's 1 2/3. So what is that? 5/3?
Well, I have a question.
Yes.
So for the, like we talked before, the upper integral should be the infimum.
Mm-hmm.
So for this part, I'm so confused. Are we trying to find the, like, so maybe supreme for the lower integral?
Mm-hmm. So for the lower integral is the supremum of the lower sums, and the upper integral is the infimum of the upper sums. Now, in practice, we're looking at those infimums and supremums are over every possible partition, so it's not really practical to do that. So instead, what we're going to do is find, in essence, a sequence of partitions, and you're actually going to prove that this works. A sequence of partitions where the upper and the lower sum keep getting closer and closer and closer and closer together. And then we just look at what the limit of that would be, and that limit is going to be our integral. So what we're starting into right here, if we go back and look at, and I should have written it down, the lower sum under that, the previous partition, what did that turn out to be? It's like 13/12.
Yep.
So 13/12, and the upper sum under the original partition came out to be
11 over 6.
how much?
11 over 6.
11/6. Okay. So if we look at what's happened here as we've gone from this partition P to this refinement P prime, the lower sum is getting bigger. It was 13/12, so it was 1, so this is, 1 and a 12th, and here we are 1 and a 6th. So the lower sum is getting bigger as I refine this partition. The upper sum is getting smaller. Went from 11/6, which is 1 5/6, to 1 2/3. And so the upper sum is getting smaller, the lower sum is getting bigger. And what we're interested in is, okay, as I keep refining this, what number do these guys get closer and closer and closer to? And that's going to be my integral. And so the definition, the theoretical definition says that we should find the infimum of the upper sums over every possible partition, but we can't go look at every possible partition. There's infinitely many of them. And so instead what we do is we find a sequence of partitions, these refinements, and we take a look at, all right, our upper sum here, basically we're creating a sequence of upper sums. So the upper sums were 11/6 and then 5/3. And then I could go do another refinement of this, throw in another point or two, and I would get a sequence of upper sums that were decreasing, that were getting smaller and smaller as I went. And then if I look at the lower sums are getting bigger. So start off at 13/12, then we go up to 7/6. And as I do more refinements, add more points to our partition, then these numbers get bigger. And then the question that we're looking at, basically what's going to happen is these guys and these guys are going to converge to the same number over here. And that number is our integral. So that's the process in practice that we would use to actually figure out what the integral is to continue to take refinements, add more points to our partitions, find the upper and lower sums, and then take a look at, okay, this is a sequence of real numbers here. What do those sequences converge to? If they converge to the same number, then we say this thing is Riemann integrable, and this is what the integral is equal to. If they don't converge, if they diverge, if they don't ever get close together, then we say that the function is not Riemann integrable. So questions about that? All right, so what we're interested in ultimately with these is for a given partition, we want to look at the upper sum. Oops, let me write it correctly. We want to look at the upper sum minus the lower sum. And if this function is integrable, that difference there should converge to 0. So if we're just trying to prove that something's integrable, we're not necessarily interested in what the integral is equal to, but we just want to prove that it's integrable. That's in essence what we need to show. We need to show that the difference between the upper sum and the lower sums tend to 0 as we refine the partition more and more and more and more. Any questions about those ideas? All right, just to get you some practice with it, there's only 4 of you, so don't know that putting you in a, well, if I put you in a group, I can let you share your screens. So let me put you out in a group. Part C of 7.2.2 asks you to find a partition so that the difference between the upper and the lower sums is less than 2/5. We're trying to get the differences between those to head to 0. So go ahead and just play with, see if you can find a partition at the moment. Let's see where we are. With this P prime partition that we just found, the difference between the upper sum and the lower sum would be, what would be that? So it would be 10 is a half, right? 3/6. So this partition here, we have a difference of a half. We'd like to get that down less than 2/5. And so you just need to find a partition that will make that happen, where the upper sum minus the lower sum would be less than 2/5. So I will put you out in a group and get it to where you can share your screens and just talk through finding a partition that would make that happen. Okay, and as soon as I leave, you should be able to share your screens if you want to. All right, any questions that came up? Everything's good? All right, so upshot is at the end of section 7.2, big theorem is that every continuous function is on a bounded interval is Riemann integrable. And that is a theorem that you want to be able to prove without referring to the book. So big idea here, every continuous function on a function on a bounded interval is Riemann integrable, which makes the Riemann integral in many respects sufficiently powerful for most real-life applications. Most real-life applications are at least piecewise continuous. And so if you can do an integral of a continuous function, that's really about all you need for most real-life applications. And so that's why the Riemann integral is the integral of choice in applications of mathematics to real life. For most of them, it's all that we need. And so you want to know that proof. You want to be able to do it without looking at the book. So make sure you go back through that proof and make sense out of it. If you have questions about it, catch me during
Which
off
theorem was it?
It is the theorem 7.2.9.
Okay, thank you.
Mm-hmm. And, you know, in some sense, you know, if you're in, unless you're into some pretty esoteric physics or chemistry, and if you're doing engineering, then basically once you have that theorem, you're done. It's like, okay, we've found an integral. It works when we need it to work. It turns out to be nice to compute. Those of you, if you've had 411, do they do integration in 411? Anybody had 411?
Yes.
What is the name of the class?
Numerical
It's
analysis?
numerical analysis.
Oh,
Anyway, when you do that, what you find out is that basically you do what we were just doing in order to actually compute integrals if you're using a computer to do it. And so in some sense, once we have that theorem that continuous functions are Riemann integrable, for practical everyday stuff, we're done. That's all we need. But we are mathematicians, and so for us, the story doesn't end there. And so the next thing is, well, what do you do if you've got discontinuous functions? And we went over it last time, but I'm going to put you out in your groups again for just a minute. And we've got our Dirichlet function, so d of x, and we define it to be equal to 1 if x is a rational number. We define it to be 0 if x is an irrational number. And question is, can you find the Riemann integral of that function? We saw last time the answer is no. So that's what you're going to find. What I want you to do is just among yourselves discuss, make sure that you understand why it doesn't work, why the Riemann integral would not work for this one. And then if you've got some questions after you've discussed it for a couple of minutes, we'll get back together and talk it through. That one. We can all prove that it's not Riemann integrable.
It was our understanding that as you take the, the lower and upper integrals don't, like the sequences of the lower and upper sums don't converge to 0 because they're always going to be like a distance of 1 between them.
Exactly. Mm-hmm. The infimum is always going to be 0. The supremum is always going to be 1. The key thing here is that since the rationals are dense, every subinterval you pick, no matter what one you pick, and no matter how you pick them, the supremum is going to be 1, the infimum is going to be 0. So the lower sum is always going to be 0, the upper sum is always going to be 1. And so there's no way that they would ever converge to each other. Very good, exactly. All right, so we've got ourselves this function that won't converge, doesn't work. But in between ones we know work, so every continuous function works. This function does not work, but these are kind of drastic contrasts. this function is discontinuous everywhere. And actually has, an uncountable number of discontinuities. It's discontinuous at every point. So the difference between being continuous everywhere and being discontinuous everywhere, obviously there's a lot that's in between there. And so that's where the real question comes is, okay, which functions in between these two are Riemann integrable, which ones aren't? Could we classify which ones aren't and which ones are? So we have that one, doesn't work. And actually, I should have been a little clearer. We're not looking across the entire real line. That's not a bounded interval. So let's, just sort of standardly, we'll just look on 0 to 1. What if we made a little modification here? And so this takes us back to the fact that the rationals are countable. And so let's take the rationals and we can enumerate them. If you remember what that means that since they are countable, that means we can associate each rational number with a natural number. So we'll choose one of these rational numbers. Again, we're looking on 0 to 1. So one of the numbers from 0 to 1, we're going to call it R1. We're going to pick a different rational number, call it R2, R3, so forth and so on, all the way out. So that's our enumeration of the rational numbers, and this thing, well, it's not equal to, obviously, but it is a subset of 0 to 1. So we're just looking at the rational numbers between 0 and 1. So if we've got that enumeration there, whatever it might be, then we can define a function on 0 to 1, and we'll define it to be 1 over n if x is equal to r sub n, and we'll define it to be 0 otherwise. Actually, let's call that f sub n. So we have these functions. There's 0 everywhere except at one of the rational points. And depending on where it falls in our list of rational points, the value of the function is just 1 over whatever the index was on that rational number that we have. Any questions about what these functions would look like or what the definition is? Okay, so then I want a new function, we'll call it f of x, that is the sum, so from n equal 1 out to infinity, of these functions here, fn of x. Now, since this is 0 everywhere except at that one rational point, and that's true for all of these, basically this thing, if we were to sort of write it out, it's going to be 0 if x is an irrational number, and then it will be equal to 1 over n if x is a rational number where it's equal to r sub n. So that's our function here. Some of these functions would look like that. Any question about the definition of f of x? All right. It looks a little bit like the Dirichlet function. The difference is that, the problem we had up here with the Dirichlet function is that your supremum was always 1, your infimum was always 0, no matter what subintervals you took. And so there was just no way that your upper sums and your lower sums were ever going to get close to each other. So the question is, do we still have that same problem down here? And maybe not so obvious, because we look at it and we say, well, the supremums now, supremum over some of these intervals is not always going to be 1. It over some of the subintervals, it's going to be 1 over n, where 1 over n is, the rational number in there that gives us the biggest number for our function. And so might it be possible that for this function, things actually converge? That we actually get the upper sum and the lower sum getting close to each other. Does that actually work? So I want you to talk that one through, think about it, see if you can, well, one, what do you think? Is it true or not? And then second one, if once you've kind of decided on whether you think it's true or not, could you actually prove either that it is true or that it's not true? So have you go back in your group again, discuss that one, and then come back and we'll see what you came up with.
Brother Cox. So would you like to know our thoughts in like a summarized version?
Of course. Yes.
Okay, so our thought process was that the sum of 1 over n does not converge. So it'll have like a similar problem to the Dirichlet function, and there'll always still be like some space between 0 and the 1 over n. We'll never converge to the same thing.
Excellent thinking. Now let's take a look at it in a little more detail. So this is our function down here, and what we're really concerned with in this, you're going to be in problem 7.2.3, you're going to be proving what we're about to use, which is the idea that if you can find a sequence of partitions that make something happen, then that's going to be true for all of the possible partitions. So even though the definition of the Riemann integral says that we're taking the infimum of the upper sums over all possible partitions, the supremum of the lower sums over all possible partitions, really, as long as we can find a sequence of partitions that makes something happen, it's going to happen for all of them. And so we really only have to look at sequences of partitions. So you're going to prove that in one of your homework problems. And so let's go ahead and use it here. So I'm going to create a sequence of partitions, so piece of K, and it's going to have M subintervals in it. So piece of K is some partition, and it's got M subintervals, which means it's got M plus 1 points. So the other way of saying this is it has M plus 1 points inside of it. So it works. And then with this, I can choose the points in my partitions, since I just have to show this as a sequence of, and now the piece of K, we're looking at refinements. So as we create this sequence, they become steadily finer and finer. So we're just adding points to what we've already got. We're not creating entirely new partitions at all. So we're doing that, but I can do that in such a way that when I look at this sum, now if we look at the lower sums, well, the irrationals are dense in 0 to 1. And so we know that the infimum of the function over any subinterval we pick is always going to be 0. And so these lower sums are always going to be 0 no matter what partition I pick. And so that means that our lower integral is going to be 0. The supremum of a bunch of zeros is still just 0. And so our lower integral is 0. So the real question is, well, can I get the upper sums to get closer and closer to 0? Can I make my upper sums as small as I want to? Now, your argument was that this is 1 over n, and if you take the sum of 1 over n, that diverges, and so we certainly can't make that arbitrarily small. And so, well, no, this shouldn't work. But there's a little catch in this. When we go and we look at our upper sum on some one of these partitions that we've picked, well, on one of the subintervals, if we look at how we've defined this thing, when n is equal to 1 here, then our function is equal to 1. And so on one of these subintervals inside of here, the function is going to be equal to 1. So our supremum is going to be equal to 1. And then we're going to be multiplying that times the width of the subinterval that that point lies in. So I'll just call that W. There are m subintervals, so I'll just call that W1. So W1 is the width of the subinterval where the point that gives me a function value of 1 happens to lie. Any questions about that? And then we would have, well, you know, we have these functions 1 over n. So worst case, there would be a different subinterval that would have the 1/2 in it, which is the next largest value this function can have. And then it would be some, you know, times the width of whatever interval it was in. And that would continue until, you know, we got out to, say 1 over m, there's m subintervals. And so worst case, the m largest numbers that this function takes on are 1, 1/2, 1/3, down to 1 over m. And let's suppose that all of those were found in different subintervals. That would be the worst possible case for this in terms of making the upper sum too big. And then I would multiply that times the width of the intervals that they're in, and I would end up with that coming out. So the question now is choosing my partitions so that the widths of these subintervals where I have these larger values are so small that this sum goes to 0. And so this is p sub k. I could choose, I can pick my points so that the width of this interval where the 1 occurs is, say, well, you know, less than or equal to, so I'll just put worst case on here, 1 over 2 to the k. And I could choose my points so that the width of the second interval, the one where the 1/2 occurs, is less than 1 over 2 to the k plus 1, and so forth and so on. And then, again, thinking worst case, so this is all less than or equal to, so actually I should put less than or equal to over here. When I get to this last one, I can have the 1 over m, and I can put it, well, it's got to have the rest of the length of the interval in it. So it would be, I didn't leave enough room, 1 minus the sum of the, you know, from j equal to k to, well, let's see, what would that be, k plus m of 1 over 2 to the k. So it would just be all of the length that didn't get taken up in these other little subintervals down here. Well, that will be less than or equal to 1, this whole thing here. And so what we've got here, if we look at this sum, this upper sum that we're checking out here, these, if I look at these first m minus 1 terms over here, all but this last one there, that would be less than or equal to just taking the sum from j equal to k to k plus m minus 1 of 1 over, not 2 to the k, 2 to the j, sorry. So that would just be, you know, since I'm taking half of that, if I just kind of ignore the half here and the 1 and those things, that's only going to make the sum bigger. And that's what I've done here, is I've just ignored those supremum values and instead looked at the widths of the intervals. And then this guy over here is, and then so I'd have plus 1 over m times this value over here. I'll just call it w sub m, which is that leftover sum, which is less than or equal to 1. And if you think about this as k goes off to infinity, So as I take this sequence of partitions and I keep refining it, I keep throwing in more and more and more points to make these subintervals smaller and smaller and smaller. This sum right here, well, that sum actually goes to 0. So that sum is going to go to 0. And the W sub m over here is always less than or equal to 1. And 1 over m is, as I get more and more subintervals, that means that m gets bigger and bigger and bigger. M is going to go off to infinity. So as k goes to infinity, m goes off to infinity. So this thing is going to go to 0 as well. And so actually, by a very judicious choice of the widths of the subintervals, I can actually force this thing, the upper sums, to tend to 0. And that would match the lower sums, and so this would actually end up being Riemann integrable. And that trick, idea, however you want to refer to it, is one that is going to show up. This is really how we deal with functions that have discontinuities when we're trying to do their Riemann integrals, is the fact that we can choose these partitions so that around the discontinuities, the big discontinuities, the ones that jump up significantly, we can force the interval around those to be so small that when you multiply the value times the interval, you get such small numbers that they really don't add up to anything. And so we can get discontinuous functions, even functions that have infinitely many discontinuities, to still be Riemann integrable if, as long as we can pull this off, where we can make the intervals around the discontinuous points so small that they add up to 0. So with that, we have to, so now we're interested in, okay, well, we've got this function up here, not Riemann integrable. We have this function, it is Riemann integrable. We have any continuous function being Riemann integrable. Now, where is the break? What is it that makes, where's the break between a function like this, which isn't Riemann integrable, and a function like this that is? And so we'll be taking a look at that towards the end of the chapter. But this little trick of picking the widths of the intervals to be so small that you can make them add up to nothing is one that shows up over and over again when you're talking integration theory. And so we needed to see it. All right, well, our time is up. If you have some individual questions, I'll hang on, I can answer those. If not, have a great day. And make sure that you look at the homework before you come on Thursday. We'll be able to spend a good portion of Thursday just answering questions about the homework, if you have those. So make sure you look at it and have some questions ready for that on Thursday.